Okay, welcome to this video on measures of position. This is the last part of chapter 3, and in this part of the chapter, we're going to learn how to describe where a particular data value is with respect to all the other data values in the sample or in the population from which it comes. So to give you an idea of where we might want to use something like measures of position, let me tell you about this car tire that lasted 36,000 miles before needing to be replaced, and an incandescent light bulb that lasted 2.2 hours before it burned out and needed to be replaced. We might ask the question, are either of these events unusual? Well, to really answer that question, we're going to need more information. So let me tell you that on average, car tires last 35,000 miles. Okay, whatever this particular brand and model is, the average for all those tires is 35,000 miles, and the standard deviation is 2,250 miles. For this particular kind of light bulb, the average number of hours that it can burn is 3.3, and the standard deviation is 0.4. So with that information, maybe we can try to answer the question, are either of the events that I described above unusual? Well, to answer that question, we're going to calculate something called a z-score. A z-score can be found by taking the value minus the mean and dividing by the standard deviation. When you do that, what the result will tell you is how many standard deviations away from the mean the data value is located. And so this is going to be a measure of position because it's telling us where this particular data value lies with respect to the mean. It's going to say this data value is so many standard deviations above the mean or so many standard deviations below the mean. So if we do the calculation for the car tire, we could take the 36,000 miles minus the 35,000, which was the mean, divided by the 2,250, and we get 0.44. So this car tire is 0.44 standard deviations above the mean. The light bulb lasted 2.2 hours. If we take 2.2 minus the mean of 3.3 and divide by 0.4, we get negative 2.75. So we could say this light bulb is 2.75 standard deviations below the mean. Now, when it comes to answering the question about whether any of these events are unusual, we have to go back to that empirical rule that we talked about in our last video. If you remember the empirical rule from the last video, we said that for normally distributed data, 95% of the data is within 2 standard deviations of the mean. Since only 5% of the data is more than 2 standard deviations away from the mean, we would say it's pretty unusual to be that far away from the mean. Now, in this case, you could see the car tire is only 0.44 standard deviations away from the mean. Not unusual at all. However, the light bulb, which is 2.75 standard deviations below the mean, is pretty far away from the mean. It's out there in that region where only 5% of the data would fall. And so we would say that's a pretty unusual thing. And so the light bulb would be considered an unusual event here if it only lasted 2.2 hours. Okay, so z-scores tell us where a data value is in relation to the mean, and we can use z-scores to determine if data values are unusual or not. Now, the assumption is that the population is normally distributed. Okay, so we'll have to make that assumption here. And if that's the case, then like I said, anything that's more than 2 standard deviations away from the mean would indicate an unusual event. Okay, we can also say that whenever the value is above the mean, the z-score is going to be a positive number. If the value is below the mean, the z-score is a negative number. If the value is equal to the mean, the z-score is equal to 0. Okay, keep some of these things in mind because we're going to see z-scores again later in the course, especially when we get to chapter 6 and 7 and 9, or some of the later chapters. I don't remember the exact numbers, but we will see z-scores quite a bit later in the course. Okay, now another way that we can talk about the position of a data value within its sample or within its population is with a percentile. So a percentile is going to tell us what percentage of data values are less than the one that we're asking about, which is represented by the letter X here. So this PX means the percentile for data value X. And the way we calculate that is we just count how many data values are less than X. We add 0.5 to that, and then divide by the total number of data values. That'll give us a decimal result, which we can convert to a percentage by multiplying by 100%. And then we round that result to a whole number percentage. Okay, percentiles are always whole number percentages. So take a look at this data here. Okay, I've got a data set with 11 numbers in it, and they're in order, which is helpful whenever you're doing percentile analysis. I might ask, what's the percentile for the number 12? Well, according to the formula, I got to count how many numbers are less than 12. So let me just highlight all the numbers here that are less than 12 and count how many there are. Looks like there's 6 numbers that are less than 12. So I take that 6 and I add a 0.5 and then divide by 11. So if I take 6.5 divide by 11 and multiply by 100%, that's 59.09. I think the 0909 goes on forever percent. I'm going to round it to a whole number percentage, which would be 59%. If I wanted the percentile for the number 6, I would just count here. 3 numbers are less than the number 6. Divide that, or add 0.5 to that to get 3.5, and then divide that by 11. Multiply by 100%, that should give me 31.81. And again, I think the 8181 goes on forever. Round that to a whole number percentage. The 8 would bump this up to a 32%. And then one more, if we did the percentile for the number 20, we would have to count all these numbers here that are less than 20. There's 9 of them. So add the 0.5 to the 9, get 9.5, divide by 11, multiply by 100%, you should get 86.363636%. Round it to a whole number percentage, that would be 86%. Now, we can also kind of flip this question around and say, instead of saying what's the percentile for a given data value, we could say what's the data value that corresponds to a given percentile. In other words, what data value corresponds to the 65th percentile, or what data value corresponds to the 17th percentile. In order to answer that kind of question, we have to calculate something called C, which I'm going to say stands for count. We'll see why in just a minute. But the count, C, is equal to N, which is the sample size, the number of numbers in the list, times P, which is the percentile that you're asking about, divided by 100. Now, when you do this calculation for the count, one of 2 things will happen. Either you're going to get a whole number or not. If you do not get a whole number, what you're going to do is you're going to round the value up to the next highest integer and then find the number in that particular position in the data set. So this is one of those cases, just like with the class width, when we were doing frequency distributions, that if you get a decimal number, no matter what the decimal is, you got to round it up. Now, if you get a whole number out of this calculation, you can just go straight to the number in that location in the data set, take that number and the one after it, and average them together. So let me show you an example of each case, just so you see how that works. So here's some data, and it has to be in order for this to work. So this data is already in order. I might say, find the value that corresponds to the 64th percentile. Well, there's 10 numbers in the list. So my count is going to be 10 times 64 divided by 100, which is 6.4. But now I have to round that up to a whole number. The next highest whole number is 7. And I'll go to the number that's in the 7th position. So number 26 is in the 7th position. Right? You just count over 1, 2, 3, 4, 5, 6. Number 26 would be in the 7th position. Find the value that corresponds to the 30th percentile. Okay, so 10 numbers in the list times 30 for the percentile divided by 100, that gives you 3. That's a whole number. So what you need to do is go to the number that's in the 3rd position, which is 10, take the number after it, and average those two. So take the 10 and the 12 and average them. 10 plus 12 is 22, divided by 2 would give you 11. So you would say 11 is the number that corresponds to the 30th percentile. Okay, so one more way that we can talk about the position of a data value, and that's with something that we call quartiles. So quartiles are going to be values that divide an ordered data set into 4 equal parts. Okay, so here's a data set. You can see the numbers that are here. What I want to do is I want to imagine that we've got a big rectangular piece of cake here, and we've just used icing to write all these numbers on the cake. What I want to do is I want to cut this cake into 4 pieces, and I want each piece of cake to have the same number of numbers on it. Where should I cut the cake? Well, if I want to cut this cake into 4 equal parts, probably the first thing I would do is cut it right down the middle, split it into 2 halves. Well, you might remember that the median is the number that will split a data set in half. So I would just find wherever the median is here and cut at that location. So that 18 that I've cut through is the median of the data set. Now, if I want to cut each half in half, basically what I would do is just find where the median is for each half and cut there. So it looks like the 10 would be the median of the left half and the 31 would be the median of the right half. So now I end up with the 4 pieces of cake, and each piece has 3 numbers on it. Well, the 3 places where I cut the cake are what I'm going to call my quartiles, Q1, Q2, and Q3. So Q2, which is the one we found first, is the median of the entire data set. Q1 is the median of everything to the left of that. Q3 is the median of everything to the right of Q2. So we can get these 3 quartiles, Q1, Q2, and Q3. Now, once we have the quartiles, we can make a graph called the box plot. And to make a box plot, you would just draw a number line here, like I've done, and then draw a box, and that box will go from Q1 over to Q3. So Q1 was 10 and Q3 was 31. So my box goes from 10 to 31. Then I split the box wherever the Q2 value is, which was at 18. And then I draw a line that sticks out to the left to the minimum, and a line that sticks out to the right that goes to the maximum. And we would call that our box plot. One of the things that you can see in a box plot is you can see which segments of the data have more variation and which ones have less. Okay, notice that the first segment here represented by that line, and even this first box here, kind of narrow, kind of small. That means the numbers in those segments of the data set are clustered kind of close together. But notice how like the last line here is pretty big. Even that box here representing the third segment of the data is a little bit wider than the other parts. So we would say there's more variation in the numbers in those parts of the data set. Okay, so that's what you can see from a box plot. You can kind of see where the variation is within a data set. Here's another data set. Remember, sometimes when you find medians, especially if there's an even number of numbers, you have to average 2 numbers together. So if this is our data, notice it's in order. Okay, I can find the median by taking these 2 numbers in the middle, 13 and 15, adding them up and dividing by 2. That gives me 14. So my Q2 value is 14, which is right in the middle of the 13 and the 15. So if I were cutting the cake, so to speak, I would have to cut in between the 13 and the 15. Now, if I take all the numbers to the left of that, there's 4 of them. To get the median of those, I would have to average the 6 and the 12. 6 plus 12 divided by 2 is 9. So my Q1 value ends up being 9. And if I take the 4 numbers to the right of Q2 and average the 18 and 22, okay, in order to get the median there, that would be 20. So my Q3 value ends up being 20. So Q1 is 9, Q2 is 14, Q3 is 20. Now, one thing that we can do with the quartiles is we could take a particular number, such as the number 12, and we can say, well, that would be in the second quartile, so the second segment of data. So that kind of gives you an idea of where that data stands. But one of the other things that we can do with quartiles is we can also identify outliers that are in the data set. So an outlier is a number that doesn't really seem to fit with the main group of numbers in the data set. In order to find outliers, we're going to have to calculate something known as the IQR. That's the interquartile range. The IQR is Q3 minus Q1. So in this data set, that would be 20 minus 9, which is 11. Basically, that represents the width of the box that's in your box plot. The numbers that are in that box, so in the middle two segments of the data set, that's what we would call the main group of numbers. Numbers that are far away from that main group are going to be considered outliers. Now, some numbers might be a little above the main group, some might be a little below the main group, nothing wrong there. But if you see a number that's way far away, well, that might attract your attention. You might say, well, what happened there? Was this just a really unusual person who happened to do really well on this exam or on this test or whatever the case was, whatever the data is you're collecting? Or was there something out of the ordinary going on? Okay? Did the person not understand the instructions correctly? Or did this person have some kind of help that they weren't supposed to have? Okay, who knows what the case might be. An outlier just might cause you to investigate a little bit more. Well, to get the outliers, there's going to be two conditions that we have to consider. Okay, we have to consider outliers that might be on the low end of the spectrum, and we might have to consider outliers that are on the high end of the spectrum. So outliers on the low end of the spectrum are going to be any numbers that are less than Q1 minus 1.5 times the IQR. So in this data set, Q1 was 9 and the IQR was 11. So if you do 9 minus 1.5 times 11, you get negative 7.5. Any numbers that would be less than negative 7.5 would be so far below the main group of numbers that we should call them an outlier. Well, we don't have any negative numbers in this data, so no outliers on the low end. On the high end, outliers are numbers that are above or greater than Q3 plus 1.5 times the IQR. So in this data set, the Q3 was 20, the IQR was 11. 20 plus 1.5 times 11 is 36.5. Now the number 50 in our data set is above 36.5, so the number 50 should be considered an outlier. That number is way above the main group. Okay, remember, the main group are the middle two segments of the data. This number is way above that main group. So we might want to do a little bit more investigation into what happened when we were collecting the data and got this number 50. Okay, like I said, all kinds of things could happen. Maybe the measurements weren't taken correctly. Maybe the person didn't follow the instructions correctly. Maybe we just have somebody who's really exceptional at whatever this task is. Okay, we would just want to investigate and find out if this is a truly legitimate data value or if something went wrong in the data collection process. Okay, so numbers that are far away from the main group are called outliers. If they're present in your data, you got to kind of investigate what's going on. They also have a tendency, like we saw last time with the range, to skew some results. And so you might just want to be aware when outliers are in your data, so that if you get some of these results, you can kind of look at them and say, well, I wonder if this has been skewed by the presence of an outlier. If it has been, then you got to kind of factor in that when you interpret what's going on within your data set. Okay, so that's the end of chapter 3. Next time, we're going to begin chapter 4, and this is when we get into the probability unit of the course. I'll see you next time in the next video.